In physical cosmology, Big Bang nucleosynthesis refers to the production of nuclei other than those of the lightest isotope of hydrogen during the early phases of the universe. Primordial nucleosynthesis is believed by most cosmologists to have taken place from 10 seconds to 20 minutes after the Big Bang, and is calculated to be responsible for the formation of most of the universe's helium as the isotope helium-4, along with small amounts of a hydrogen isotope deuterium, the helium isotope helium-3, and a very small amount of the lithium isotope lithium-7. In addition to these stable nuclei, two unstable or radioactive isotopes were also produced, the heavy hydrogen isotope tritium and the beryllium isotope beryllium-7. But these unstable isotopes later decayed into 3He and 7Li, as above. Essentially all of the elements that are heavier than lithium and beryllium were created much later, by stellar nucleosynthesis in evolving and exploding stars. Characteristics. There are two important characteristics of Big Bang nucleosynthesis. The era began at temperatures of around 10 eV and ended at temperatures below 100 keV. The corresponding time interval was from a few tenths of a second to up to 103 seconds. The temperature-time relation in this era can be given by the equation, where T is time in seconds, T is temperature in eV and G is the effective number of particle species. This expression also shows how a different number of neutrino flavors will change the rate of cooling of the early universe. It was widespread, encompassing the entire observable universe. The key parameter which allows one to calculate the effects of BBN is the baryon photon number ratio, which is a small number of order 6×10^10. This parameter corresponds to the baryon density and controls the rate at which nucleons collide and react. From this we can derive elemental abundances. Although the baryon per photon ratio is important in determining elemental abundances, the precise value makes little difference to the overall picture. Without major changes to the Big Bang theory itself, BBN will result in mass abundances of about 75% of hydrogen-1, about 25% helium-4, about 0.01% of deuterium and helium-3, trace amounts of lithium, and negligible heavier elements. That the observed abundances in the universe are generally consistent with these abundance numbers is considered strong evidence for the Big Bang theory. In this field, for historical reasons it is customary to quote the helium-4 fraction by mass, symbol Y, so that 25% helium-4 means that helium-4 atoms account for 25% of the mass, but only about 8% of the nuclei would be helium-4 nuclei. Other nuclei are usually expressed as number ratios to hydrogen. Important parameters. The creation of light elements during BBN was dependent on a number of parameters. Among those was the neutron-proton ratio and the baryon-photon ratio. Neutrino-proton ratio equals, neutrons can react with positrons or electron neutrinos to create protons and other products in one of the following reactions, N plus E plus A anti-I1/2 E plus P, N plus I1/2 E A P plus A. At times much earlier than 1 second, the NP ratio was close to 1:1. As the temperature dropped, the equilibrium shifted in favor of protons due to their slightly lower mass, and the NP ratio decreased. These reactions continue until expansion of the universe outpaces the reactions, which occurs at about T equals 0.7 eV and is called the freeze-out temperature. At freeze-out, the neutron-proton ratio was about 1/6. However, free neutrons are unstable with a mean life of 880 seconds. Some neutrons decayed in the next few minutes before fusing into any nucleus, so the ratio of total neutrons to protons after nucleosynthesis ends is about 1/7. Almost all neutrons that fused instead of decaying ended up combined into helium-4, due to the fact that helium-4 has the highest binding energy per nucleon among light elements. This predicts that about 8% of all atoms should be helium-4, leading to a mass fraction of helium-4 of about 25%, which is in line with observations. Small traces of deuterium and helium-3 remained as there was insufficient time and density for them to react and form helium-4. Baryon-photon ratio equals, the baryon-photon ratio, I, is the key parameter determining the abundance of light elements present in the early universe. Baryons can react with light elements in the following reactions: P, N, plus 2 hours a, 3 He, 3 hours, plus a 4 He. It is evident that reactions with baryons during BBN would ultimately result in helium-4, and also that the abundance of primordial deuterium is indirectly related to the baryon density or baryon-photon ratio. That is, the larger the baryon-photon ratio, the more reactions there will be, and the more efficiently deuterium will be eventually transformed into helium-4. This result makes deuterium a very useful tool in measuring the baryon-to-photon ratio. Sequence: Big Bang nucleosynthesis began a few seconds after the Big Bang, when the universe had cooled sufficiently to allow deuterium nuclei to survive disruption by high-energy photons. This time is essentially independent of dark matter content, since the universe was highly radiation-dominated until much later, and this dominant component controls the temperature-time relation. The relative abundances of protons and neutrons follow from simple thermodynamical arguments, combined with the way that the mean temperature of the universe changes over time. If the reactions needed to reach the thermodynamically favored equilibrium values are too slow compared to the temperature change brought about by the expansion, abundances would have remained at some specific non-equilibrium value. Combining thermodynamics and the changes brought about by cosmic expansion, one can calculate the fraction of protons and neutrons based on the temperature at this point. The answer is that there are about 7 protons for every neutron at the beginning of nucleosyntheses. This fraction is in favor of protons, primarily because their lower mass with respect to the neutron favors their production. Free neutrons decay to protons with a half-life of about 10.2 minutes, but this time scale is longer than the first 3 minutes of nucleogenesis, during which time a substantial fraction of them were combined with protons into deuterium and then He4. The sequence of these reaction chains is shown on the image. One feature of BBN is that the physical laws and constants that govern the behavior of matter at these energies are very well understood, and hence BBN lacks some of the speculative uncertainties that characterize earlier periods in the life of the universe. Another feature is that the process of nucleosynthesis is determined by conditions at the start of this phase of the life of the universe, and proceeds independently of what happened before. As the universe expands, it cools. Free neutrons and protons are less stable than helium nuclei, and the protons and neutrons have a strong tendency to form helium-4. However, forming helium-4 requires the intermediate step of forming deuterium. Before nucleosynthesis began, the temperature was high enough for many photons to have energy greater than the binding energy of deuterium. Therefore any deuterium that was formed was immediately destroyed. Hence, the formation of helium-4 is delayed until the universe became cool enough for deuterium to survive. After which there was a sudden burst of element formation. However, very shortly thereafter, at 20 minutes after the Big Bang, the universe became too cool for any further nuclear fusion and nucleosynthesis to occur. At this point, the elemental abundances were nearly fixed, and only change was the result of the radioactive decay of some products of BBN. History of theory The history of Big Bang nucleosynthesis began with the calculations of Ralph Alpha in the 1940s. Alpha published the Alpha-Beta-Gamma paper that outlined the theory of light element production in the early universe. During the 1970s, there was a major puzzle in that the density of baryons as calculated by Big Bang nucleosynthesis was much less than the observed mass of the universe based on calculations of the expansion rate. This puzzle was resolved in large part by postulating the existence of dark matter. Heavy elements Big Bang nucleosynthesis produced no elements heavier than beryllium, due to a bottleneck, the absence of a stable nucleus with 8 or 5 nucleons. This deficit of larger atoms also limited the amounts of lithium-7 and beryllium-9 produced during BBN. In stars, the bottleneck is passed by triple collisions of helium-4 nuclei, producing carbon. However, this process is very slow, taking tens of thousands of years to convert a significant amount of helium to carbon in stars, and therefore it made a negligible contribution in the minutes following the Big Bang. equals helium-4 equals. Big Bang nucleosynthesis predicts a primordial abundance of about 25% helium-4 by mass, irrespective of the initial conditions of the universe. As long as the universe was hot enough for protons and neutrons to transform into each other easily, their ratio, determined solely by their relative masses, was about 1 neutron to 7 protons. Once it was cool enough, the neutrons quickly bound with an equal number of protons to form first deuterium, then helium-4. Helium-4 is very stable and is nearly the end of this chain if it runs for only a short time, since helium neither decays nor combines easily to form heavier nuclei. Once temperatures are lowered, out of every 16 nucleons, 4 of these combine quickly into one helium-4 nucleus. This produces 1 helium for every 12 hydrogens, resulting in a universe that is a little over 8% helium by number of atoms, and 25% helium by mass. One analogy is to think of helium-4 as ash, and the amount of ash that one forms when one completely burns a piece of wood is insensitive to how one burns it. The resort to the BBN theory of the helium-4 abundance is necessary as there is far more helium-4 in the universe than can be explained by stellar nucleosyntheses. In addition, it provides an important test for the Big Bang theory. If the observed helium abundance is much different from 25%, then this would pose a serious challenge to the theory. This would particularly be the case if the early helium-4 abundance was much smaller than 25% because it is hard to destroy helium-4. For a few years during the mid-1990s, observations suggested that this might be the case, causing astrophysicists to talk about a Big Bang nucleosynthetic crisis, but further observations were consistent with the Big Bang theory. Deuterium equals. Deuterium is in some ways the opposite of helium-4 in that while helium-4 is very stable and very difficult to destroy, deuterium is only marginally stable and easy to destroy. The temperatures, time, and densities were sufficient to combine a substantial fraction of the deuterium nuclei to form helium-4 but insufficient to carry the process further using helium-4 in the next fusion step. BBN did not convert all of the deuterium in the universe to helium-4 due to the expansion that cooled the universe and reduced the density and so, cut that conversion short before it could proceed any further. One consequence of this is that unlike helium-4, the amount of deuterium is very sensitive to initial conditions. The denser the initial universe was, the more deuterium would be converted to helium-4 before time ran out, and the less deuterium would remain. There are no known post-Big Bang processes which can produce significant amounts of deuterium. Hence observations about deuterium abundance suggest that the universe is not infinitely old, which is in accordance with the Big Bang theory. During the 1970s, there were major efforts to find processes that could produce deuterium, but those revealed ways of producing isotopes other than deuterium. The problem was that while the concentration of deuterium in the universe is consistent with the Big Bang model as a whole, it is too high to be consistent with a model that presumes that most of the universe is composed of protons and neutrons. If one assumes that all of the universe consists of protons and neutrons, the density of the universe is such that much of the currently observed deuterium would have been burned into helium-4. The standard explanation now used for the abundance of deuterium is that the universe does not consist mostly of baryons, but that non-baryonic matter makes up most of the mass of the universe. This explanation is also consistent with calculations that show that a universe made mostly of protons and neutrons would be far more clumpy than is observed. It is very hard to come up with another process that would produce deuterium other than by nuclear fusion. Such a process would require that the temperature be hot enough to produce deuterium, but not hot enough to produce helium-4, and that this process should immediately cool to non-nuclear temperatures after no more than a few minutes. It would also be necessary for the deuterium to be swept away before it reoccurs. Producing deuterium by fission is also difficult. The problem here again is that deuterium is very unlikely due to nuclear processes, and that collisions between atomic nuclei are likely to result either in the fusion of the nuclei, or in the release of free neutrons or alpha particles. During the 1970s, cosmic ray spallation was proposed as a source of deuterium. That theory failed to account for the abundance of deuterium, but led to explanations of the source of other light elements. Measurements and status of theory. The theory of BBN gives a detailed mathematical description of the production of the light elements deuterium, helium-3, helium-4, and lithium-7. Specifically, the theory yields precise quantitative predictions for the mixture of these elements, that is, the primordial abundances at the end of the Big Bang. In order to test these predictions, it is necessary to reconstruct the primordial abundances as faithfully as possible, for instance by observing astronomical objects in which very little stellar nucleosynthesis has taken place, or by observing objects that are very far away, and thus can be seen in a very early stage of their evolution. As noted above, in the standard picture of BBN, all of the light element abundances depend on the amount of ordinary matter relative to radiation. Since the universe is presumed to be homogeneous, it has one unique value of the baryon to photon ratio. For a long time, this meant that to test BBN theory against observations one had to ask, can all of the light element observations be explained with a single value of the baryon to photon ratio? Or more precisely, allowing for the finite precision of both the predictions and the observations, one asks, is there some range of baryon to photon values which can account for all of the observations? More recently, the question has changed. Precision observations of the cosmic microwave background radiation with the Wilkinson microwave anisotropy probe and Planck give an independent value for the baryon to photon ratio. Using this value, are the BBN predictions for the abundances of light elements in agreement with the observations? The present measurement of helium-4 indicates good agreement, and yet better agreement for helium-3. But for lithium-7, there is a significant discrepancy between BBN and WMAP Planck, and the abundance derived from population 2 stars. The discrepancy is a factor of 2.4 or 4.3 euros below the theoretically predicted value and is considered a problem for the original models, that have resulted in revised calculations of the standard BBN based on new nuclear data, and to various re-evaluation proposals for primordial proton-proton nuclear reactions, especially the abundances of 7b, n, p, 7 Li versus 7b, d, p, 8b. Non-standard scenarios. In addition to the standard BBN scenario, there are numerous non-standard BBN scenarios. These should not be confused with non-standard cosmology. A non-standard BBN scenario assumes that the Big Bang occurred, but inserts additional physics in order to see how this affects elemental abundances. These pieces of additional physics include relaxing or removing the assumption of homogeneity, or inserting new particles such as massive neutrinos. There have been, and continue to be, various reasons for researching non-standard BBN. The first, which is largely of historical interest, is to resolve inconsistencies between BBN predictions and observations. This has proved to be of limited usefulness in that the inconsistencies were resolved by better observations, and in most cases trying to change BBN resulted in abundances that were more inconsistent with observations rather than less. The second reason for researching non-standard BBN, and largely the focus of non-standard BBN in the early 21st century, is to use BBN to place limits on unknown or speculative physics. For example, standard BBN assumes that no exotic hypothetical particles were involved in BBN. One can insert a hypothetical particle and see what is to happen before BBN predicts abundances that are very different from observations. This has been done to put limits on the mass of a stable tau neutrino. See also: Big Bang, chronology of the universe, nucleosynthesis, stellar nucleosynthesis, ultimate fate of the universe. References. External links. For a general audience Weiss, Acham. Big Bang nucleosynthesis, cooking up the first light elements. Einstein Online. Archived from the original on February 8, 2007. Retrieved February 24, 2007. White, Martin, Overview of BBN, Wright, Ned, BBN, Big Bang Nucleosynthesis on arXiv.org, Burles, Scott. Knowlett, Kenneth M. Turner, Michael S. Big Bang Nucleosynthesis, Linking Inner Space and Outer Space. ARXiv, Astro pH/9,903,300. Technical articles Burles, Scott, and Kenneth M. Nolet, Michael S. Turner. What is the BBN prediction for the baryon density and how reliable is it? Viz. Reverend E63, 0635512. AR Ziv, Astro pH/000845. Bibcode, 2001 PHRVD 63F3512B doi, 10.1103/Phys Rev D63.063512. Report No. Fermilab Pub 00-239 Jedam Zeke, Carson, Non-Standard Big Bang Nucleosynthesis Scenarios. Max Planck Institute Far 1/4 Astrophysique, Garching. Stigman, Gary, Primordial Nucleosynthesis, Successes and Challenges AR Ziv, Astro pH/05115534. Forensic Cosmology, Probing Baryons and Neutrinos with BBN and the CBR AR Ziv, Het pH/03093447. And Big Bang Nucleosynthesis, Probing the First 20 Minutes AR Ziv, Astro pH/03072444, RA Alpha, HA Beth, G Gamma, The Origin of Chemical Elements, Physical Review 73, 803. The so-called I plus or minus I squared I cubed paper, in which alpha and gamma suggested that the light elements were created by hydrogen ions capturing neutrons in the hot, dense early universe. Beth's name was added for symmetry, Gamma, G. The Origin of Elements and the Separation of Galaxies. Physical Review 74, 505. Bibcode, 1948 PHRV. 74505 G doi, 10.1103/Physrev. 74.505.2. These two 1948 papers of Gamma laid the foundation for our present understanding of Big Bang nucleosynthesis, Gamma, G. The Evolution of the Universe. Nature 162, 680. Bibcode, 1948 Nature 162 680 G doi, 10.1038/162680 AO. Alpha, RAA Neutron Capture Theory of the Formation and Relative Abundance of the Elements. Physical Review 74, 1737. Bibcode, 1948 PHRV. 74.1737A doi, 10.1103/Phys Rev 74.1737. RA Alpha and A. Herman, On the Relative Abundance of the Elements, Physical Review 74, 1577. This paper contains the first estimate of the present temperature of the universe. Alpha, R.A. Herman, R. Gamma, G. Evolution of the Universe. Nature 162, 774. Bibcode, 1948 Nature 162 774A doi, 10.1038/162774 BO. Java Big Bang Element Abundance Calculator.